Thank you. So I'm back, Andrew Freeman, assistant professor at Baylor University. This is a collaborative work with Amar Risk and Mikhail Rudolph from Leibniz University, Hanover. We have, this paper is under review. There will be a link to the full paper at the end if you're interested. But yeah, so introduction to point clouds, different than sort of the 360 or stereoscopic video we were just talking about. So these are offered as a compelling representation for telepresence applications in particular. They can be recorded with high-speed RGBD cameras or multi-camera arrays. So pretty difficult to capture point clouds right now, but it's getting easier and easier every year. Some downsides to point clouds, though, are that they have extremely high data rates. So one single point cloud frame could be 20 megabytes uncompressed, and the compression is very, very difficult and very slow. So a standard encoder could take 500 milliseconds per frame. So you guys thought that VVC is slow. Point clouds are way, way behind that, generally speaking. And all of these challenges make low latency streaming very difficult, which is important to address if we actually want to use these for telepresence applications in the future. So again, I'm not going to really go into the streaming protocols. We're all familiar. But a quick thing that we're going to talk about with MoQ that we're leveraging in this work is the idea for priorities on the quick streams, and we'll get into that here. And what we're really trying to explore is a new method for adaptation. So with things like Dash and HLS, adaptation is usually client-side. It's what I like to call explicit adaptation. You make a decision about what quality level you want to receive. And here we are exploring what I call implicit adaptation, where the client doesn't make a decision, the server doesn't make a decision. We're actually passing off that decision to the transport layer. And we'll kind of see how that starts to work. So this is an overview of our system. We'll get into the main components here. But we have a publisher sending point cloud data, and then we have multiple subscribers that have different latency tolerances. And they interact with MoQ to receive different quality levels. So we're leveraging multiple description coding here. This is something that's been explored pretty widely in past video coding literature, never really took off. But for point clouds, at least at this stage, this point in time, offers a lot of benefits because encoding time for point clouds scales pretty dramatically with the number of points. The number of points can change from one frame to the next depending on how much motion is happening, how much occlusion there is. So it's very hard to have a steady bit rate anyway. So what we're doing here is we just randomly sample the source point cloud into a bunch of different complementary partitions, and then we can encode those in parallel. So then we overcome the half second of encoding latency. We can start to encode these frames in real time as they're being produced. And then unlike with SVC, which right now is impossible with point clouds, nobody's created a codec for this yet. The decode order doesn't matter, which can be beneficial in this kind of system. And then with MoQ, we're just mapping our different partitions to separate MoQ tracks. So if we have 10 partitions, we'll send those across 10 MoQ tracks, and then the subscriber will subscribe to all 10, but not necessarily get all of that data. We'll see how that works. So we allow the subscriber to sort of define a pseudo latency target. And this is actually mapping to the MoQ delivery timeout, which is in the specification draft currently. And this basically just determines how long an object, in this case a frame partition, can persist at the relay before being transmitted to the subscriber. And then we're also leveraging the priorities within MoQ, which map to the quick stream priorities. And this allows us to give higher precedence for certain tracks of data if there's network congestion. It makes it more likely or less likely that data will actually be passed through when network congestion occurs. So essentially with our setup, we're just telling MoQ to send as much data as possible within the latency target, and any data that cannot be sent within that target is just dropped. So we can maintain live, but within our latency tolerance. So this is our experimental setup. We use the Microsoft voxelized upper bodies data set, which has been around for a while. It's 512 cubed resolution. So it's a lot of data. And then we looked at a couple of different parameters for the number of partitions to use for our sampling, the GOP size, which has some bearing on like when a track can sort of be rejoined, and several different delivery timeouts and fixed bandwidth limitations. And we wanted to compare this to the adaptation mechanisms in traditional ABR streaming. So we used a VV Dash implementation for point cloud streaming on Dash, but we had to use offline encoding and packaging because getting multiple description coding to work with traditional streaming kind of requires much more complex packaging, and it could not keep up with real time at all. So we really just want to compare the best case scenario explicit ABR for something like Dash with our implicit adaptation with MoQ and see how those work in comparison. We used our random uniform sampling strategy, and this is based on Luke Curley's implementation of MoQ Lite, but all of the mechanisms that we use are shared between MoQ Lite and the other spec compliant MoQ implementations. One thing we did have to do though was implement the delivery timeout mechanism ourselves. There's been some debate about this in like the MoQ working group about how to actually do this. Our concerns were, honestly, I'm not exactly sure how delivery timeouts are meant to be used or what the thought is behind the design of this, but I saw this in the spec and I was like, okay, I think we could use this for some implicit adaptation. So we're not actually doing the full spec definition, which kind of requires some insight to what the transport layer is doing or what the quick implementation is doing. We're basically just using this as a way of time stamping frames as they get received by the relay, and then if the frame is still there when we're trying to send it off and our delivery timeout threshold has been surpassed, we just drop it and continue on to the next frame. So it's kind of a naive implementation, but for our purposes, it actually seems to work pretty well, which is encouraging. And we just kind of use this as a proxy for the end-to-end latency. So our experimental results, there are a lot more details on this in the paper, of course, but we found kind of the best all-around performance configuration within our testing environment. And we found a pretty straightforward latency quality trade-off, which is what we were hoping to see, so this is encouraging. It's essentially, as you allow higher latency by just increasing this one parameter, this delivery timeout, then you automatically receive higher quality, which is great. So we don't have to do any explicit ABR decisions on the client setting which quality we want to get. We just say, hey, I can tolerate 100 milliseconds of latency instead of 50. I'll get more data, higher quality. Or if you can tolerate half a second of latency, you'll get way higher quality. And so there's an example here, going from 50 to 500 milliseconds at 600 megabit per second bandwidth yields a 90% increase in throughput, which has a direct bearing on quality, as we'll see. And in comparison to the Dash experiment that we did, we looked at 4 different ABR algorithms that VV Dash provided, and the bandwidth-based algorithm performed the best, and it approached MoQ in terms of the overall throughput, but there are some downsides to this, as we'll see on the next slide. But even still, MoQ with its implicit adaptation performed better overall under like the best configuration with 10 partitions and a GOP size of 30 frames. So one of the interesting things that we saw was Dash, as we know, kind of has a slow warm-up period with most ABR algorithms. So you're trying to measure how the network is doing and slowly ramp up so that you don't immediately have buffering or have a slower start time. So whereas Dash has this slow ramp up in terms of the amount of data it receives, with MoQ in our implicit representation, we actually get pretty close to our maximum bandwidth like straight away, because it's just trying to blast out as much data as possible, dropping data that can't be delivered within that time. So we can actually saturate the connection much more quickly, immediately have very, very high quality. The downside, though, is we could have a stalling scenario if bandwidth is highly limited and we have too much congestion. So that's kind of an area of future work, is how to mitigate stall scenarios or avoid them altogether. There are a lot of tricks we can play, but this is just kind of an early work at this stage. Then we took a look at developing a proof of concept for integrating saliency and content-aware partitioning in our system. So we used a segmentation model called PointNet and trained it to detect the head region within our data set. And essentially, we're now leveraging the priorities within MoQ tracks. So we can sample the head region, which is probably what people are more interested in, sample that with a higher rate and put that into the highest priority track here on the bottom. And then when there's network congestion, we're going to be much more likely to get that highly salient head data than the other points. So this video on the right shows the same configuration, the same network conditions, and we're just changing the sampling strategy using naive random uniform sampling and then our content-aware sampling and the MoQ prioritization. And we get roughly the same amount of data coming through, but it can be much higher quality for this type of application, much more aligned with what people are interested in focusing on. And interestingly, this has a bearing on the VMAF score as well, which I imagine does not like all the big holes that come into play with random uniform sampling. And so the next steps with this work, again, this is still pretty early stages. We want to look at mitigating the stall scenarios, like I said, do a full comparison to something like LL- or LLHLS, and then, of course, train and evaluate better segmentation models. The one that we showed worked really well for this video and then not very well for some of the other videos. So that's why it's just a proof of concept. And then also think about other applications that we can leverage an implicit adaptation scheme for, right? What else can we maybe do something better than explicit ABR, use similar techniques, really benefit from MoQ prioritization, those sorts of things. So if you have any ideas, let me know. We can chat about it. But this is what we've looked at so far. If you want to read the full paper, it is up on archive. There's some formatting issues with the paper, but all the content's there. But you can give it a read if you want some more details. All right, thank you.
Thank you very much. Room for one single question, if there is one. If not, I may have one. If you compare to ABR dash, obviously there's many different ABR algorithms that could be used and that could also warm up sooner, right?
Yes.
So you used, what did you use?
We used, there were 4 that were implemented in VV Dash that were kind of inspired by the ones that were provided in Dash.js, but they're not necessarily exactly the same. But we started with those 4, and we're going to expand that in the future.
Okay, because you're operating outside of a realm in the bit rates out of any realm that has been considered, I think, in that software.
Exactly.
Yeah. Anyway, thank you very much, Andrew.
Thank you.